Yeah, so you're able to see the question now on the whiteboard.
Just 1 minute.
Yeah, this is one of the questions you sent me, na beta?
Yes, yes. Sir, I'm looking for the answer.
You got the answer?
No, I'm checking the answer for
Don't worry. Let's first understand the question. So, are you clear on how to solve it, or the problem is only with the answer key? And is the method clear in the question, beta? So it says a steel bar of length L, width B, and depth D is loaded at the center by a load W. Then the sag in the beam is equal to how much? Okay, so is the method of the question clear?
Yes, sir. There is a bar and at the center of weight of W is loaded.
Yes, that. Okay. So you understood the question, right?
Yes.
How will we do the question? Have you figured that out?
No, sir. I tried to do, but
okay. So I'll explain what we have to do. So first, let's understand with the diagram. Okay, how it will look. So yeah, now we'll be getting the whiteboard. So I'm explaining how we'll do the question. So for example, this question is something like this. Just a second. Yeah. So this question is something like this. You have, let us say, initially the bar is like this. Okay. There's nothing loaded onto it. And it's between two walls like this. And this bar has all these properties. It has what all is given to us. Natural length is given to us, right? And the side of the bar, it's like this sort of a bar. So it has this dimension D and this dimension B. It has, like, let's say, a rectangular sort of cross section. Okay? So this is how it looks when there is no load on it. Okay? Now next, what we are doing is we are putting a load of W at the center, and the Young's modulus of the bar is also Y, and B and D are also given. And next, what we are doing is when we are putting the load, as a result of that, we'll have to assume that the bar sags. So attaching the load at the center, so the bar sags like this. As a result of that, so let's say it becomes something like this. This is an exaggerated drawing, which assumes it's not so thick. It's more like a thin wire kind of thing, but it has a rectangular kind of cross section. So as it sags, like this, it sags because of the weight that we put at the center. That weight is, let's say, like this. We attached it with something, like a rope or something like this. Okay. So basically, what is happening now is that each of these sections are L by 2. Okay. More or less. It's actually, you can say it is like L prime by 2, because this would have sagged. So L would be equal to L plus delta N. Like this. And this is a weight of W. Okay, so now if you look at the forces which are acting, okay, so that is the important thing now. So the forces which are acting at this point are tension like this. So this is what we have to investigate. Okay, so now what else is given to us? That it's sagged by a certain amount. That is given. Oh, we have to find the amount of sag. Okay. Then the sag of the beam, of the bending of the beam is equal to how much? So what we mean by sag is we have to find out here
delta L.
So this distance. No. Delta L is the extension meter. What we have to find is the sag. This distance. Okay, let us say it is some delta X. This distance we have to find out.
Okay.
Have you understood this now? So okay, that's so actually, you have to now understand like this. So at that center point, the FBD is weight acting downwards and tension acting like this. Okay. Where let us say that the angle that the tension makes with the horizontal, that is theta. Okay. So we have obviously 2t sine theta is equal to W, and we'll assume theta is a small angle.
Yes.
So if we assume theta is a small angle, we'll say that okay, 2t into theta is approximately equal to the weight. Okay, so that's my first equation. Okay. Now next what we have to do is we have to come back to the geometry of this problem and understand the relationship between theta and the other thing. So if you look at the geometry of this, I'm just making it below here. So my sag thing, this is like this. But assume of course that theta is small, which I have not drawn over here. I have drawn theta as a large value, but assuming that theta is small. So I've got this over here. Now the important thing is to work out the geometry of this thing. How we'll get the relation between theta, L and L plus delta L. Okay, so if I now draw a supporting line like this one, in fact, you can show that this length from here to here, this is equal to how much? This is L. Whereas this is how much? This is L prime by 2 and this is L prime by 2. Okay. And further over here, or by this is not required. Here only in this diagram you can show that these two angles are theta. Okay, so that's how we'll eliminate theta. And this over here is my delta x. Alright, so this is the thing. So theta is approximately equal to delta x divided by L by 2. You can take tan theta. So it is approximately 2 times delta x divided by L. That is my theta. So now my next part of the equation. So this becomes like my second equation. That theta is approximately equal to 2 delta x divided by L. Okay. So now in the above equation, I can eliminate theta. Now the next thing is tension. So for tension, we have to understand that.
That would be L prime, na? 2 delta x.
Sin theta, it's more or less the same. Okay, so we can say theta is approximately tan theta, which is approximately sin theta.
Okay, yeah.
We can get away with that. Now we come to the longitudinal stress upon longitudinal strain is equal to Young's modulus. So that is where my L prime will come. Okay, so my longitudinal stress will become tension divided by the area, which was B into D, because the cross section was like that, divided by the longitudinal strain, which is delta L by L, and that should be equal to Young's modulus. So tension as usual is equal to AY, that is B into D, that's the area, into Young's modulus, divided by L into delta L. Okay. Now this is like my third equation. Now in this, I have to substitute delta L in terms of delta X. Okay, then everything is done. So how to substitute delta L in terms of delta X? So this is where you can see that L prime, which is L plus delta L, is equal to what? It is twice of that hypotenuse. So that is L by 2 whole square plus delta X square. And of course, we understand that delta X is very small compared to L, or L by 2 for that matter. So binomial approximation. Okay. So 2 times we can take L by 2 outside. So square root of 1 plus 2 times delta X by L ka whole square. So that is my L prime, which is L plus delta L. So this, now we'll use the binomial approximation. So L plus delta L is approximately equal to L into 1 plus half of this will become 1 plus half into this. So that is 4 delta X square divided by L square. Understood this step? Now the power half is coming inside.
Yes, sir.
Right?
Yeah.
Okay. So L plus delta L is approximately becoming L into 1 plus 2 times delta X ka whole square divided by L square. So delta L is approximately equal to how much? Compare both the sides. So it is 2 times delta X ka square divided by L. Right. So there you go. So that is like my third equation. Okay. So tension, which is EY, that is BD by L into delta L, is now approximately equal to EY by L into 2 times delta X square by L. So like this. Okay. And we had earlier that tension into theta. So this is after substituting in the second equation. This we are getting by substituting in equation 2. And now we will substitute this in equation 1. So equation 1 was like this: T into theta was equal to, 2T into theta was equal to W. So 2 times this area into Young's modulus into 2 times delta x square divided by L square. Okay, that's the tension into delta theta. Into theta. Now, what was theta? Theta was approximated itself as 2 delta x by L. Okay, so
2
delta x by L. Yes. So this should be equal to what? My W. So there you are. Now we have the equation that delta x cube into this whole term, which is 4 times BD into Young's modulus divided by L cube is equal to W. So the sag will become like this. The sag delta x should become L into cube root of this whole term. Okay, cube root of W upon 4 times B into D into Young's modulus. Something like this should be the answer.
So, but in the options, there is no power of 1 by 3 actually.
Just one thing, you have to check the
Sir, I think we have to take just another approximation. Like, can you slide up the board?
yeah. No, the only thing here that can be different is if they are asking for some other quantity instead of the sag, because just a moment, huh? My other whiteboard computer has gone offline. Okay. But just try the calculation yourself, and I'll put up again. Okay. Right. So let's resume and let's take a look at this question again. So it is saying that toy cart length L, circle of radius 2L, the time period is T. If it is speeded up till the horizontal circle of radius 3L with the time period T1, then the relation between T1 and TV you have to find out. Okay, so let me put this on the whiteboard. Share here. Right, so what is happening is, if in general, let us say this thing is rotating like this, where the radius is actually equal to L plus X, where X is the amount of extension. Okay. Then what is happening is, we can say that the tension in the wire is given by the general formula, the equivalent spring constant, that is Ay by natural length multiplied by the extension, and that tension has to be equal to mv square by r, and this is now tension. Okay, T over here is tension, so don't confuse it with time period. So on the one hand, we have the relation that Ey upon L into X is equal to mv square upon r, which is L plus X. Now, this is my equation 1. Now, on the other hand, I have the equation that time period, that is let's say small t, that is 2 pi r by v. So time period is proportional to L plus X divided by v. That is like my second relation. And from equation 1, you can see that v square is proportional to what? It is proportional to L plus X into X. Rest of the things are constant. Area, Young's modulus, natural length, and mass are constant. So we can proportionality. So from this we can see that what is the relation of time period with this? Time period is proportional to L plus X upon V, which itself is proportional to what? Square root of L plus X into X. So that is your relation of time period. Time period is proportional to square root of L plus X upon X. This is how we can do the question now. So in one case, your time period is t1, let's say, or t, when the x is equal to L, because the total length was 2L. Okay. And in the other case, your time period, let's say, is t2, and that is when your total length was 3L. So this is L plus 2L upon 2L. So from that, you will get the ratio of t1 and t2. Right? Is this clear, Vita?
Yes, yes.
I'll just minimize it for a moment for you. Okay. Right. So that is a couple of your questions, Kritika, and Arman, I'll just come to your questions. Just hang on a second. Now, before that, there is one more question of Kritika's that I want to solve first. Right. So this solution is clear, right? You understood this?
Yes.
Yeah. So hope this solution is clear. Okay. So can I remove the solution now?
Yes, yes, sir.
You understood the method, Beta?
Yes, I have
Okay.
noted down.
I will send you the whiteboard. Okay, good. So I am now again sharing another one of your questions. Okay. So this one now. See, question number 9, right? This one.
Yes.
Okay. So let's understand the question. So it's saying that we have a magnetic field inside a long solenoid having n turns per unit length and carrying current I. Where the iron core is kept, it is okay. Current I. Wait. Magnetic field is B when the current is I. When iron core is kept. Achha. Okay. It's saying if the magnetic field is B in general, and when the iron core is kept, where the iron core has a susceptibility of chi, that X kind of symbol, it is called chi, then how much is the magnetic field you're going to? So this is just about that application. So I'll just put up the whiteboard again. So this is just a minute. Stop share here and start the share. Right. So this is that kind of question which has to do with the relationship of relative permeability with this thing, susceptibility, and from that the magnetic field. So I'll just quickly relate the important formula over here, because a lot of the time, people overlook these formulae. So what happens is that if there is some magnetic field created by some external agent, like a current carrying wire or something like this, in a certain region, if we have a certain magnetic field which is, let's say, like this, uniform magnetic field, or even non-uniform for that matter, if the external magnetic field is B, so this is the magnetic field created by the external agent. So this is the external field. And then what we do is, in that region, suppose we place some magnetic material, like a ferromagnetic material, typically like soft iron over here. Now this is, let us say, a ferromagnetic material. Okay. Which has susceptibility given by the symbol chi. And typically for ferromagnetic materials, chi is very large. It can be a number like 50 or 60 or something like that. So then what happens is that there is an induced field which is created because of the the magnetic domains aligning with that. So that is, let us say, the internal induced field, and that becomes how much? That becomes susceptibility times the external field. Okay. So actually there's a more complicated formula of this. First we write the external field divided by mu naught. So that gives us the magnetization, the external magnetization. Then we multiply the external magnetization with chi. So that gives us the induced magnetization. And then you again multiply the induced magnetization with mu naught. So that becomes the induced field and all that. But without getting into that much technicality. So what happens, therefore, the net field, now this induced field is along the external field. Unlike in the case of electrostatics, where the realignment of the dielectrics, dipole regions, they create a internal field which opposes the external field. But in the case of magnetization, it actually supports the external field. So the net magnetic field, which in fact is the vector sum of the external field plus the induced field, it actually in magnitude it becomes the scalar sum. So it becomes 1 plus chi. Sorry, 1 plus chi.
Sir, your B net is internal or external?
Sorry, B is the external. Okay, capital B is the external, and BIN is the induced field. Okay, this is the field because which is induced by. Okay, so this is a field which is induced by the domains, induced by realignment of the magnetic domains in the magnetic material. There's only one case in which the induced field actually opposes the external field. And in that case, we say chi is a negative quantity, and that is in the case of diamagnetic material. But it's like that. So this is ferromagnetic given to a soft iron. So this will become 1 plus chi times the external field. So this is the concept that we are using now. So if for example we have that solenoid, now solenoid के core पे अगर कुछ नहीं है, like it's this kind of thing, then we know that the magnetic field at the core of the solenoid is just mu naught into Ni. Okay. But if we put some magnetized material in the core of the solenoid, so now the core of the solenoid is filled with some material like a soft iron core like this, and this has a permeability constant mu. I mean a relative permeability of mu r. So what happens is that we also sometimes say that there's some unit vector n caps. Okay. So this becomes how much? It becomes mu times Ni into n cap, where that mu is actually relative permeability into permeability of free space, okay, into Ni. Okay. And that relative permeability you will see is nothing but chi. Okay. So this is the net, whereas this was the external. Okay. So when you compare the two, you can see that this term is actually equal to 1 plus chi.
So both are external.
Both are
external field.
No, B net is the net field. You understanding? So B net, which is the net field, is actually becoming how much? You can see because it is 1 plus chi. Na? Relative permeability is 1 plus chi. So your B net is replace your mu r with 1 plus chi, okay, into mu naught Ni, na? In that direction. So it is basically mu naught Ni plus susceptibility times mu naught Ni. Okay. So it is effectively nothing but, so mu naught Ni is the external field and this is the induced field. Okay. And their sum is the net field. Okay. So basically what happens is if you just compare the net field with the magnetic material, with respect to the field just because of the external agent and no material in between, okay, in air, you can also see like this. Okay, you just take the ratio of their mods, that is nothing but 1 plus chi is to 1, or that is what we define as the relative permeability. Just like you have the dielectric constant being a dimensionless quantity, you have the relative permeability. So this is the concept that is. So I'll just minimize this for you to complete, and next I will get to one of the questions from Arman, and I'll come back to your. So this first. All right. So is this clear so far, beta?
Sir, can you pull it down?
Yeah. So you will find these formulae and the definitions of all these things: susceptibility, permeability, relative permeability, or etc. The most convenient place to study it from is from H.C. Verma Part 2, the chapter called Magnetic Properties of Matter.
Yeah,
It's
sir.
given in very short. कुछ आपको extra read करने की जरूरत नहीं. It's very useful, and whatever is required for JEE mains. All these things are not there in JEE Advanced. Okay? Only JEE mains and CET. Typically, they ask in CET a lot of these things.
Okay.
Okay, so this is fine now?
Yes.
Alright. So I'm just going to move on to the next question we'll solve. For that, stop the share here. Start the share here. Okay. So this 34th question, right, Arman?
Yes, sir.
Okay, so let's go through the question. I'm not sure you are getting it clear enough in your screen. It depends on the resolution. But anyway, I'm reading out the question. So it says that we have two particles X and Y of equal mass and with unequal positive charges. They are free to move and are initially far away from each other. So they have equal mass but charges, let's say Q1 and Q2, and they are very far away and they are free to move. That means there's no other type of force on them. Okay. With Y at rest, X begins to move towards it with the initial velocity of U. So after a long time, we have to find what happens over here. So Arman, what are the principles you applied in the question?
Momentum conservation.
Very good. And
Energy conservation.
Yes, energy including the electrostatic potential energy of the pair. Okay, so your concepts are clear. Now, let us understand what will happen. Okay. So, because the masses are same, so can this thing happen? Can X stop while Y will move with the velocity of U? Because initially X was given the motion. Do you think this thing can happen?
Yes. No.
Why?
Sir, is the answer B?
B, which is X and Y will both move with a velocity U by 2 each after a long time. Not necessarily. I'll explain why. And X will stop and Y will move with a velocity less than U. That's also not correct. Both will move with velocities less than U by 2. That's also not correct. So let's understand whether A is correct or B is correct. Okay, I think it is quite clear that C and D cannot be correct, because if their masses are equal, so if X stops, then Y must have the momentum of M into U. So how can its velocity be less than U? So that's not possible. And similarly, both will move with less than U by 2. So system's momentum will become less than initial momentum. So that's also not possible. Okay. So let's try to understand here. So
either of B or C is correct, no?
Either of A or B will be correct, because you'll understand C is definitely ruled out. C क्यों नहीं हो सकता है देखो, because दोनों का mass same है. So if X stops, Y will have to move with U. The question is whether X will stop or not. Okay. You understanding my point? Because if X stops, then we are definite about one thing, that the momentum of the system has to remain mu, no? Okay. So it will not be possible that okay. So let's. Just. Yeah. So let's say they are very far apart initially, and this is Y and this is X, and they are having charges plus Q1 plus Q2, but mass is same, M and M, and initially this is what is happening. This is moving with a velocity U towards it. Okay. So after some time, let us say this is what has happened. X has come a bit closer, okay, comparatively. So X is here now, and Y has moved away a little. So let's say Y is over here. So by now the distance between them has become some X. Whereas earlier the distance was tending to infinity. My diagram isn't very much to scale. Assume X has come much closer and Y has only moved a little bit. And by then their speeds are like this, V1 and So the equation that we definitely know that mv1 plus mv2 has to be equal to mu. That's one equation we know for sure. And we also know that half m v1 square plus v2 square plus k q1 q2 by r is equal to half mu square. That's like a second equation. Okay. But we have to also understand that they're always repelling each other. Okay. So what will happen is, so the force vectors, they are always looking like this. So if the force vectors are always looking like this, that means this guy's velocity is always decreasing and this guy's velocity is always increasing. This is how the mutual repulsive force is looking. So if you think of how V1 is behaving as a function of time, V1 is all the time decreasing and V2 is all the time increasing. So what is happening is that initially V1 is equal to U and V2 is equal to 0. Okay, then let's say after some time, let's say at some time T1, V1 has become something like, let's say, let's say it's become 2U by 3. So at that point of time, V2 will have to be U by 3. So you see what is happening here, they are still approaching each other. But here also they are approaching each other. Why? Because V1 is greater than V2. Now let's say at a certain instant of time T2, V1 becomes U by 2 and V2 also becomes U by 2. So that is the time when they have come to closest approach. Okay, this is the time when they are closest to each other because their relative velocity is 0. Okay, and then after that it comes to a stage where this one becomes smaller because it's continuing to decrease, V1. So V1 becomes, let's say, U by 4 and now V2 becomes 3U by 4 and they are now starting to separate. Okay, and that process will continue. Okay, so that process will continue till what happens? Till the force becomes 0 again, till the interaction stops. Okay. That separation of that thing of V1 continuing to decrease and V2 continue to increase, this will happen till what? The interaction stops. That means the distance between them again tends to infinity. So that means these two equations that we've written earlier, equation 1 and equation 2, if we make r tending to infinity, then it will give us the solution of what happens finally, okay, when they stop interacting. So if you put r equal to tending to infinity in that, you actually get a pair of solutions. Okay, so substitute this r tending to infinity in equation 2. So equation 2 actually becomes like this, that half m v1 square plus v2 square is equal to half mu square. Or in other words, v1 square plus v2 square is equal to u square. And you also have equation 1, which is that v1 plus v2 is equal to u. This is coming from momentum conservation. This is from equation 1. So this and this now become a pair of equations which helps you solve for v1 and v2, and that gives you a quadratic equation. Okay. So now remember that in this form we are solving for which situation? We are solving for the situation when r tends to infinity again. So the pair of solutions you will get will be these. They are quadratic sets. So the pair of solutions you will get will be either v1 is equal to u and v2 is 0. Okay, but this is not. This is the initial case. Or what happens is the exchange. v1 becomes 0 or v2 becomes equal to e. This is what is happening when they again become infinitely. This was initially when they were infinitely away, but x was moving and y was stationary. This is when y starts moving and by then x becomes stationary. So which option becomes correct? I think the first one, right? That was what it was saying. So I've done a lot of working in this, but at certain stage this will not be required so much working. It will be quite obvious to you.
Yes, sir.
So this kind of timeline and this working is not required. You will be quite used to this kind of thing if you've done these type of questions with 2 blocks and a spring attached in between, or those type of questions also. So like over there, the spring force would be repulsive, and if the masses of the 2 blocks would be same, then after a while the first block would come to rest, the second would be moving with you. Then the whole sequence would change. Okay? The first one would start increasing, the second one would start decreasing. Because as the spring extends, it also applies a attractive force. But here there's only repulsive force. So that thing doesn't happen. Once they reach that infinite distance again, there's nothing else happen. Now the separation keeps increasing. But from infinity also it keeps increasing, because y will keep moving at v and x will just remain stationary where it is. Okay, so this was this question. Now I'll move on to the second question by Arman.
सर
Yes.
सर वो जो t इज इक्वल टू t1 t2 t3 में जो आपने वेलोसिटी लिखा है वो सेम डायरेक्शन में है क्या?
हाँ,
दोनों? ओके.
वो no, that is just out of an assumption that at certain time, if this one is v by 4, that one has to be 3u by 4. Why? Because of momentum conservation.
Okay.
No, so you can see that the force is always repulsive. No? So the particle y speed is all the time increasing. So it will increase in what kind of sequence? It will go from 0 to u by 4 to u by 2 to 3u by 2 to 3u by 4 to some final value. Similarly, the other one is always slowing down. So it is decreasing from u to 3u by 4 to u by 2 to u by 4 to finally some value. So finally some value क्या है वो अपने को निकालना है. So that is how we realize in the question that the final value is basically when their distance becomes infinite again. So that is the end of the sequence here. So this process of v1 decreasing and v2 increasing, it's happening till when? Till the interaction between them stops. So that happens when r tends to infinity.
Okay, sir.
Understood now? Okay.
Yeah.
Okay. So now I will come back to another question. Yeah. So Arman's next question I'm coming to. Yeah. Just hang on a second. Okay. So you should be, this is a 39th question you asked for, right, Arman?
Yes, sir.
Okay, so let's take a look at this question next. So what is happening here is we have a particle of mass 1 kg and given charge 1/3 of a microcoulomb. It is projected towards a non-conducting fixed spherical shell having the same charge uniformly distributed on its surface. Find the minimum initial velocity of the projection required if the particle just grazes the shell. Okay, so yeah, so this is a question where what is happening, you will realize that because it's a non-conducting shell, so what is happening, uska charge distribution change nahi hone wala because of the proximity of the particle. If it had been a conducting shell, then as the particle is coming closer, it would have affected the charge distribution, right, because of induced charge concept. But here there are no free electrons and all, so the distribution of charge on the surface remains intact. That means the electric field of the shell, that always remains intact. It's always a repulsive kind of field radially generated from its center. So the direction of force that is happening, that is acting on that particle as it is moving, what is the direction of that force? It's a central force. No? It is always along r cap with respect to the center of the sphere.
Yes.
And it's always q1 q2 by r square r cap. So if you take the center of your sphere as your origin, then you will see that the direction of force on the particle which is moving is central. It is always along r cap, which means what is happening? The torque because of that force is zero. So its angular momentum will be conserved. You getting my point? The sphere को आपने fixed रखा है, so origin आपका fixed है, और वो fixed origin के हिसाब से what is happening? The force vector on your moving particle, it is always acting along that r vector or along that r cap unit vector. So it's creating change in momentum, and you can see from the direction, the force is such a way that it provides both centripetal kind of force or normal kind of force, which causes the particle to turn, as well as it creates a tangential component of force, which actually causes the particle to decelerate as it is coming. So उसका deceleration भी हो रहा है और वो particle turn भी हो रहा है. But both the things are happening in such a way that is angular momentum remains conserved. So the conservation principles we'll have to apply here are conservation of angular momentum and conservation of energy. So it's a very good question. Just try this out. I'm putting up the solution on the board and I'm explaining the concepts also. So question is clear to both of you, right? So I'm just unsharing this and moving on to my whiteboard. I'll put up the question there. So don't worry. So the general idea is over here like this, that it's like, your particle is moving in a fixed electric field, which is because of that shell, which is fixed and it's non-conducting in nature. So my So I'm defining this as my coordinate frame. Z-axis is also coming out. So I'm defining the center of my sphere as my okay. Now this is having charge which is embedded on the surface, and that charge cannot shift because it's a non-conducting sphere. So let's say this is a sphere having charge plus q and radius r. So now when I have some particle which is sitting over here having a charge, let's say q and mass m, that particle, if its position vector with respect to the sphere center is the vector r. ये position vector मेरा r है अगर. So you can see that the force that this shell is applying on it will always be in this direction. It's repulsive. I'm assuming both are positively charged. Okay. So this will be the force that this applies on it. So as this particle now moves, like let's say right now, its velocity vector is like this. So its momentum vector is like this. Okay. But as you can see, the force is providing both centripetal or normal component of this thing as well as tangential deceleration. So the particle will tend to go in this kind of a path. Okay, this is not an accurate representation of the question you've given me because there the particle was here and it's moving like this. So I'll come back to that. But if this is how the particle is located at t, so after some time at t plus delta t, let's say it's located here and its velocity is changed to some v prime. Okay, and its position vector has changed to some r prime. This is changed to some r prime. This angle can be anything. Okay, so the force has changed and all that. So what we will see over here is that angular momentum, because the force is a capital Q into small q by r square, r cap.
So can you explain?
Yes, tell me.
Sir, can you explain the last line of the question?
हाँ, I'm coming to that. But first you concentrate on what I'm saying over here. तो ये particle जहाँ पर भी है, उस पे force कैसा लग रहा है? Force ऐसे formula के लग रहा है. So the direction of the force is along r cap, and the magnitude is 1 by r square. So the force is proportional to r cap by r square, which means that it is a central force. Okay, and that means that it is a conservative force also. So that's the first thing, and the second thing is that it means r cross f is 0. Because r cross r cap is 0. So what is happening? That the second thing here means, so the first thing means that potential energy, electrostatic potential energy plus kinetic energy of the particle is conserved. And what the second thing means is that angular momentum of the particle, okay, with respect to the origin, that is conserved. So these are the two conservation principles we apply. Okay. So first let's understand these two. Then I'm coming to the particular question and we'll understand how to apply these in that question. Okay. So given that your sphere or your shell, whatever, is fixed, and also the charge on the sphere is remaining always fixed because it is non-conducting in nature. So it will always apply a force which is given by this function, where r is the instantaneous position vector. So force is always proportional to r cap upon r square. That means the work done by the force is independent of path and it's a conservative force. And more importantly, it means the torque because of that force with respect to the center of the sphere, that is r cross f, is 0 on the particle. Okay. By the way, they should over here be a null vector. Okay. So the torque about the origin, which is the center of the sphere, is 0. So that means that the angular momentum of the particle, this is for the particle with respect to the origin, which is the center of the shell, is conserved. That quantity is conserved. Okay. So those are the conservation principles that will be applied over here. Now let us come back to what the question is saying. So I'll just put up the relevant diagram with respect to the question now. So question के केस में क्या हो रहा है? My sphere is over here. Let's say, oops. Let's say this is the sphere with the center of the sphere being here and all that, and my particle is somewhere here. It's having an initial velocity like this. Okay. So all this is given to us. The sphere's radius is equal to 1 millimeter, and the line of action of this one's velocity, or this particle's momentum, let us say along this direction. Okay, so m charge q and this velocity v is along this direction. So this perpendicular distance additionally is given. Okay, so that distance d is given to me as 0.5 millimeter. And now we have to find the condition, and also let's say that this is having a charge of plus capital, which is, so now I think we have to find the condition on something, either v or distance or whatever. Okay, so initially I think the distance is very far. The minimum initial velocity required for it to graze the shell. Okay. So the question is now asking, so since nothing is given about the initial distance, you assume that this initial distance from the center to the particle is very large. Okay. Now we have to find minimum value, magnitude of that v, so that the particle at least grazes. Grazes means it touches the surface. Okay, this way. So you'll realize that अगर particle को enough momentum नहीं दिया है, it will go in a path like this. I'm just showing it with a red line. There's one possibility that the particle goes off on a path like this. So this is not what we want. We want it to actually at least reach the surface. So the path that we want for the particle is that it should go on a path like this. It should at least just about graze over here. That is something that we want. Okay. So now you have to solve that. Understood? So the particle just about grazes the surface. That means it's touching the surface tangentially and going away. So wherever it touches the surface, the direction of its velocity should be along what? It should be along the tangent. So 90 degrees to r. So if the velocity of the particle when it's touching the surface is, let's say, v prime, so उसका angular momentum कितना हो जाएगा? mv prime r, because that angle will be 90. Whereas this initial angular momentum you can work out. So conserve the angular momentum, that's one equation, and conserve the energy. So when the particle reaches the surface, the energy is k capital Q into small q divided by r. Whereas the initial gravitational potential energy is tending to 0. Because, sorry, electrostatic potential energy is tending to 0 because the distance is tending to infinity. So equate the sum of kinetic plus electrostatic potential energy and you'll get the solution. So this is quite a nice question, and just work it out. I'll put up the solution in a moment.
सर बट अगर वो टेंजेंशियली टच करके जा रहे तो वहाँ पे रिपल्सिव फोर्स भी तो होगा ना.
हाँ वही हो रहा है ना, रिपल्शन की वजह से ही तो टच करता हुआ चला जा रहा है. अगर अट्रैक्टिव होता तो देन तो इट वुड कम एंड क्रैश अगेंस्ट द सरफेस ना. अगर अट्रैक्टिव होता तो उसका पाथ ऐसा, द बेंड वुड नॉट बी लाइक आई हैव शोन फॉर द रेड कलर डॉटेड लाइन और द ब्लैक कलर. इट वुड बी द अदर वे. इट वुड बी अट्रैक्टिव फोर्स टुवर्ड्स द सेंटर. सो its path would be different. No, it's because of the repulsion that is happening. But whether the repulsion is enough to make it, go completely away from the sphere like the red line, or the repulsion ke hote hue bhi it's just coming and touching, or it might even crash against the sphere. That all depends on the initial momentum. No? It's the interplay between the repulsive force and the initial momentum. If you've given it too much momentum, it will anyway come and crash. It will not come along the straight line path, but it will still come on a curved path and crash against the surface. If you given too little momentum, it will never come even near the surface. Pehle hi wo chala jayega, like the red colored line. So we want something in between. Neither it crashes onto the surface, nor it completely avoids the sphere. It just about, touches the surface.
Okay.
Tangentially and moves. Okay, so hope the trajectory is clear now. Okay. Now just write the two equations and try to work this out. Okay, I'm putting it up on the board in just a moment. Just try it out. Okay, so initially the energy of the system is half mu square, because the distance r between them is tending to infinity. Okay. And the angular momentum of the particle with respect to the center of the sphere is how much? It is mv into d, because it is linear momentum into momentum, that concept that we are learning that day. So it's basically like this, that if the position of the particle is here, but the velocity of the particle is, let's say, like this, then your angular momentum about the origin is r cross mv. The origin being this point over here, but that also means that just draw this. This is not this particular question. In this particular question, that perpendicular distance is r by 2. But whatever this angle theta is, the angle between these two is actually 180 minus theta. But sine of 180 minus theta is the same thing as sine theta. Okay. So the angular momentum becomes mvr sine of, in my diagram, pi minus theta. So that is mvr sine theta. So that is nothing but mv into d, where d is, you drop this perpendicular on this line of action, and this distance. So this is the general theory of angular momentum. So that is why in this case it is this, where d is actually r by 2. If you go back to the diagram, d is r by 2. So that is the case initially. Now similarly, I want you to work out what is happening, assuming that this particle takes that path more or less like the black colored line I've drawn, but it's just a bit closer. It's just, just about touching grazing the surface over there. So if that is happening, then what is the case? So anyway, now from here, let us say the particle goes on a path like this, and somewhere here it grazes the surface. So where it grazes the surface, let's say its velocity vector has become v prime, and its position vector, as you can see, is going to be r prime, which will just be r, and this angle will be 90. So at this point of time, over here, what is the angular momentum with respect to the origin? It is mv prime r. And what is the energy? It is half mv prime square plus k. This one is small q. The charge on this is, let's say, capital Q. Divided by. So this is this. Okay. So now applying the conservation principles. Angular momentum about O. So you can see your mvd should be equal to mv prime r. So you'll realize that v prime is v into d by r. So in this case, d was 0.5 millimeter and r was 1 millimeter. So your speed of the particle as it is grazing is actually half of the initial speed. And that
Yes, I got the answer.
Different. And secondly, apply the energy conservation. Very good. So you get this thing. So half mv square should be equal to half mv prime square plus k q cube divided by capital R. So that's your second equation. And in this now you just substitute what you're getting from the first equation. This one was your first equation. This one is your second equation. And now just substitute the information that you're getting from here and you'll get the answer. You get the condition for grazing. So what that condition for grazing will tell you is that if you give a initial V of less than the value you're getting here, is going to actually never come even close to the sphere. It will veer off at a larger distance. So it will not tangentially touch the surface. It will always remain at some distance from the surface. Whereas if you give a V more than this, then instead of tangentially just touching the surface and going off, it will actually crash against the surface. Right, so this is the principle. So always remember that when you're talking about gravitational force or electrostatic force, particularly related with a shell or a sphere or something like that on a particle, and the shell or sphere is remaining fixed, then the angular momentum remains conserved. That's a very important thing. Just like in orbital motion also, elliptical orbit in gravitation, angular momentum remains conserved. It's the same reason, because the force you're dealing with is a central force. Okay, so I'll just minimize this for a moment and leave you with this, and in the meantime I'll pick up the next question we are doing. So next I'm going to go back to one of Kritika's questions. Okay, I'm putting it up on the board in a moment. Right, so Kritika, this was one of the questions, right? 17th one.
Yeah.
So assuming the expression for the pressure exerted by a gas on the walls of a container, it can be shown that pressure is related to what kind of power? 1/3 kinetic energy per unit volume, 2/3 kinetic energy per unit volume, etc. Now again, since they have not explained which type of gas they are talking about, we have to assume we are going to the ideal gas model of kinetic theory of gases. And you'll remember that in the original ideal gas model, we had assumed that they were tiny particles. So those tiny particles are basically what type of particles? They are monoatomic gas molecules. So we'll assume that the degrees of freedom are 3. Okay. So the kinetic energy per volume, per unit volume, हम कैसे निकालेंगे? By just using the formula of this thing. Okay. So understand what the question is asking. It's asking for the relation of pressure with respect to the kinetic energy per unit volume. Okay. So that's what the question is about. So I'm now moving on to my whiteboard, and we'll see how we'll develop this relationship. Okay. It's actually, this question is just about understanding the correct relationship from kinetic model of ideal gas. Okay. There's not much else to it. So we want to relate the pressure. We want to relate the pressure exerted by a gas on its walls with respect to the kinetic energy per unit volume. That kind of. So you know that the pressure has the relation that PV is equal to nRT. Since we are talking about per, or you can also write this as PV is equal to total number of molecules into Boltzmann constant into T. They're one and the same thing. That's one equation we have. And the other equation that we have is that the RMS speed is equal to square root of 3 PV divided by N into capital M, or we can also write it as square root of 3 PV divided by capital N into small m. That is number of molecules into molecular mass, or number of moles into molar mass, whichever. Or we can further also write this as VRMS is equal to square root of 3 RT by M, which is the same thing as 3 KT divided by molecular mass, small m. So we have all these relations. Now what we want to do is we want to relate pressure with kinetic energy per unit volume. So let's understand how we are doing that. Okay. So let us say that in the total volume V, we have n number of moles, okay, and the pressure of the gas is P and the temperature is T. So what is the total kinetic energy? Okay. We can write it as total number of molecules into half m VRMS square, or we can also write that as number of moles into Avogadro's number, okay, into half m VRMS square, because this is the average kinetic energy per molecule. Okay. So, average kinetic energy per molecule according to kT-jee. Otherwise it is F by 2, but here we'll write it as 3 by, so anyway, that I'll come to, but that is half m VRMS square. Okay. There's no rotational or vibrational involved here, so assuming that. Okay, so that is this thing. So the total kinetic energy, as you can see, and this all should actually be quite clear to you. I'm just writing it as a derivation again, but so this can be written as n into Avogadro's number into molecular mass by 2 into VRMS square. So it can be written as number of moles into half molar mass into VRMS square. Now, where molar mass is that thing, it is 32 grams for oxygen, 2 grams for hydrogen, like that one kind of quantity. So this is the total kinetic energy of our sample of gas, which has what properties? It has a pressure P, volume V, temperature T, and number of moles N, and of course molar mass is N. So that is the total kinetic energy of our sample. So now our kinetic energy per unit volume is becoming this thing. It is N into half M VRMS square divided by the total volume. Now I want to relate this quantity. I want to relate this with what? I want to relate with pressure. So how do I do that? So I understand that VRMS is equal to what? It is square root of 3 PV divided by N into N. So substitute that over. Okay. So first of all, the total kinetic energy, which is half N times half M VRMS square, you will see this is nothing but the formula of internal energy. It will become N CVT, which is nothing but N 3 by 2 RT. Because we are dealing with the ideal monoatomic gas, so degrees of freedom is 3. Okay, so this is coming from the fact that VRMS is square root of 3 RT by N. Okay. So in other words, the total kinetic energy of a sample of molecules is nothing but its internal energy. This is the principle of thermodynamics. So we could have skipped all these steps here. We could have just directly said that this total kinetic energy is the internal energy of the gas sample, okay, which is equal to this N CVT on N. Okay. So there you are. So kinetic energy per unit volume, which is what we are trying to calculate, will be basically what? Internal energy per unit volume. So that is 3 by 2 nRT divided by volume. And nRT is nothing but what? Pressure into volume. So it is PV divided by V. So it is 3 by 2 times the pressure. So this is the relationship between what we are looking for, kinetic energy per unit volume with respect to pressure. Is this clear, Kritika?
आपने वो conclude कैसे किया था कि kinetic energy, internal energy?
यही तो प्रिंसिपल ऑफ थर्मोडायनेमिक्स है ना बेटा. सी इंटरनल एनर्जी ऑफ अ गैस क्या होता है? it is the total kinetic energy of its molecules, because there is no other type of energy involved, because there is no intermolecular bond, so there's no bond energy. So that is how we get that relation. This is equal to number of molecules into degrees of freedom into half kT. So this is the general thing. Okay, and therefore our delta U comes as N R F by 2 delta T, and that's why finally your CV comes as F by 2R. So ये सारा जो derivation है ना वो यहीं से आता है. It comes from all these things. So that the quick way of doing this question at the exam level is they were asking you what is the relationship between pressure versus kinetic energy per unit volume. So in other words, they are basically asking you the relation between pressure versus internal energy per unit volume. And internal energy is basically what? It is NCVT, because delta U is NCV delta T. So it's NF by 2 RT. And you can replace nRT with what? Pressure into volume. So it is the same thing as F by 2 into pressure into volume. Okay. So this. So you substitute that over here now. And that's it. You're done. So that's the concept.
Sir, इसमें actually answer B option दिया है 2/3.
Okay. So substitute this over here. So pressure is equal to what? So internal energy per unit volume is कितना आ रहा है? It is F by 2 into P. So it should be directly proportional. Okay. So I'm coming back to the question. I haven't read all the options. So anyway, the options are saying the first option is 1/3 of kinetic energy per unit volume. The other is 2/3. The third is 3/4 and like that. So here it just take F as what? 3. Take the degrees of freedom as 3, because you're talking about, I mean, they haven't not said which type of gas. So you're assuming it's a monoatomic gas.
Okay. So which option?
Understood?
B option, no?
हाँ, so देखो, हाँ, so देखो, internal energy per unit volume will be 3 by 2 P. So P is how much? 2/3 of that. So B option is that.
Okay.
All right. Okay. So now next I'm coming back to one of the questions which Arman has said. Okay. Okay, so 10th question, let us look at this one. So it is a relation between 4 equal positive charges are fixed at the vertices of a square of length L. Z axis is perpendicular to the plane of the square. The point Z equal to 0 is the point where the diagonals intersect, so it's the centroid. Then the plot of electric field versus the distance Z. Okay, now this is a very typical type of question for which I can give you a very nice shortcut way of solving. Okay, so first just read through the question, both of you, and make sure you understand it properly. In fact, start by making a diagram. So what is happening is your 4 particles which are having equal charge, they are fixed actually in the XY plane at the corners of a square. And for that XY plane only, your origin is nothing but the centroid of the square. And the Z axis is therefore perpendicular to the centroid. So in other words, it becomes the symmetry axis which is perpendicular to the plane of the square. So first of all, understand that diagram. Okay. Then I'll explain what is the easiest way of doing the question.
This is done by correlating it with a ring or something like that, right?
वैसे कर सकते हैं यार. You can just what I would suggest rather than that is first you have a symmetry. Because of the diagram symmetry, you'll understand that the field is purely along the Z axis at any point on the axis. Yes. So your field is like this. Your E vector is Ez k cap. So what you can do is whenever you have a situation like this, use the property of field as potential gradient. So Ez is minus dV by dz. So that becomes the easy way of solving. Even for a ring, we do that. The shortcut way of remembering the formula of electric field due to a ring, kya karte hain? Potential is very easy to calculate because all the charge is equidistant from any point on the axis. So use that property.
Okay.
You understanding now? The only thing is we have to understand that see, formula is not required in the question, but we have to relate it with some kind of formula. So side length is L and theta. So let's work it out that way. Okay. So let's see how we can very quickly, actually at the exam level only, that fast we can develop a formula and from that explain the behavior. And yes, you will be ultimately able to correlate this with the ring, because you'll see that the formula you will get will be very similar to the formula you have for a ring. Okay, so let's say this is my system of axis. This is my XY plane, let's say, and relate my Z axis like this. Let's say X, Y is my Z axis. Okay. So my square is now lying in the XY plane. So I'll draw my square separately. Not exactly a square, but anyway. So in the XY plane, suppose these are my 4 particles, plus Q, plus Q, plus Q, and plus Q. So you can even see, you can write coordinates for them. For example, if the square is L by L in dimension, so ये वाला particle is lying in the first quadrant of the XY plane. So it will have coordinates of plus L by 2, comma plus L by 2, comma 0. Similarly, this will be minus L by 2, plus L by 2, comma 0, like this, and like that for this and this. Now you consider any point over here. Any point over here which is at a general coordinate 0, 0, z. So you'll realize by symmetry over here that the electric field at this point, because of these 4 charges, will be like this. The direction of the electric field will be like this. So the electric field will be given by some purely z component times E. So the easy way to calculate that magnitude of the field is nothing but the magnitude of the z component, which will become minus dB by dz. Instead of del, it will become dB by dz, because you will get your potential as purely a function of z. It will not be a function of x and y. Okay. So to understand the potential now, you have to just understand the distance of all these particles from this point. So they are all equidistant. So if this distance is r, then here this distance is also r. So it basically becomes a regular pyramid, that diagram, that shape. So that r is how much? That you can figure out. That r is going to be square root of z square plus that diagonal ka half ka square.
L
So
square
square
by
of L, yeah. So the diagonal will be how much? L root 2. So L root 2 by 2 ka whole square. So that is L square by 2. This is the kind of thing. Okay. So your potential at the point P further, at this point P over here, the potential is becoming 4 times the potential due to each charge. So that is 4 times AQ positive divided by R. So it is 1 by pi epsilon naught Q divided by root of Z square plus L square by 2. This is your potential. Now you'll remember ring के लिए potential क्या होता था? KQ divided by root of Z square plus R square. So you see the similarity. So it's like that. So basically, if you've taken a ring of total charge 4Q and radius equal to how much? RL by root 2. So if you've taken a ring which had a net charge of plus 4Q, but a radius equal to how much? Half the diagonal, you would have got the same thing. You would have got this one. So your field magnitude, which is becoming minus at P, is becoming minus dB by dz. And why the minus sign is important here is this is actually the component of the field. This is actually Ez. So plus or minus becomes important. The sign will here show you that is pointing along the positive z axis. So anyway, so my z component of field is going to be minus d by dz of this term. Q upon pi epsilon naught 1 by root of z square plus L square by 2. So this is a very familiar formula. Okay, so as you can see, this will become Q by pi epsilon naught minus bars already here. So into minus half into z square plus r square, which is basically L square by 2 over here, to the power minus 3 by 2 into 2z. So to the power 3 by 2. Now actually we have to do the analysis of graph. So in that sense, it becomes an application of graph theory and all that, maximum minima. But I think from your theory notes, you should remember the behavior of field with respect to distance for a ring, and that same behavior will now apply over here. So you'll remember the maximum of field occurs at which point? R by root.
R by root 2.
So it's just a matter of maximum minima. So in case you've forgotten all that, you can just apply the maximum minima theory here. But you'll realize here that at z equal to 0. So I'll tell you a trick also. Suppose you don't remember the graph directly, you can still understand the behavior of the graph this way. That you're wanting to plot your E, which is basically Ez, versus your Z. Okay. Now understand the behavior at the two extremes. So if you go back to the above formula, you'll understand that in this formula, for Z being very small compared to L by root 2, okay, Z square plus L square by 2 can be approximated as L square by 2. Okay. So for very small values of Z, so this is basically for small values of Z, or Z tending to 0 basically, Ez is becoming directly proportional to Z. So the denominator में Z square is neglected. Okay. So that means at the beginning of the graph, it should behave like a straight line proportional to Z. It should be something like this. Now the initial behavior of the graph should be like a straight line like this, proportional to Z. Whereas on the other hand, for Z being very large compared to L by root 2, is the other way. In the denominator now, you will neglect that term, L square by 2. Okay, so Z square plus L square by 2 can be approximated as Z square. So the whole denominator for large values of Z can be approximated as Z cube. So Z upon Z cube, so it is basically Q by Z square. So basically for large distance, Z being very large compared to L by root 2, your field will become directly proportional to 1 by Z square. It basically behaves like a particle. So it should have this kind of a behavior. So your overall function now, you'll realize, is changing behavior like this. It is starting like something like a linear function, but somewhere it will have to reach a maxima and then go towards this. It will have to have that hyperbolic behavior. And if you work out actually this maxima, which actually is a value you should remember, at least for JEE Advanced level, this maxima occurs at Z equal to R by root 2. So in this case, it will become L by 2 actually, because R itself is like this.
L by
so this is an information that you can just remember over here, so it's always helpful. So where you have your theory notes for all the derivations in electrostatics, now you should always keep this graph and this behavior of electric field with respect to distance in mind for this.
Okay.
So I'm just minimizing this for a moment for you guys, and in the meantime, I'll move on to another question. So first, let me go to the relation between potential and field, then we'll come back to this.
सर मैंने आपको ईमेल में एक क्वेश्चन भेजा है.
Okay, so I'll go through that next. Just give me a moment. This one you're not able to prove that the current. This
Yes,
question,
yes,
beta.
yes, yes.
Minimum is LC parallel. Okay, I'll explain. Just a moment, okay. Okay, so this next thing it is related to actually. She has asked about a situation where we have one branch in a circuit which is an LC oscillator parallel to another branch which is some kind of load, like let's say some resistance or some devices or something connected to an AC source, and we have to understand that in which case the current through the given load, that is the given device or resistor which is in parallel with the LC oscillator, should be minimum. Okay, so how that current will be minimum when we are satisfying the this thing condition, the resonance condition. So let's, I think that's the question you are referring to, Kritika. Have I understood the question correctly?
Yes, sir.
Okay. So let's say we have some kind of situation like this. Okay. Now, you know, the thing is, practically when we talk about LC oscillator, the branch having no resistance at all presents a problem, because in real life that doesn't happen. So we'll assume that at least the connecting wires in our circuit to the branch which has the inductor and capacitor have some resistance. That resistance might be negligible, that's fine. So we'll neglect it, or we'll say it's very small. But let's assume even this branch has a bit of resistance. Okay? So let's say that resistance is small r, like an internal resistance, it's very negligible. This is the inductor L and this is the capacitor C. Now this is connected in parallel across something which is like a load, or which is like some device, or some electrical appliance that we're using. So that's the load resistor, and this is connected across a AC source. So what we have to prove over here is that my current through the load will be minimum when the AC source is satisfying the condition of resonance for the above circuit, that is the LC oscillator in the above circuit. So this is the case. So let's understand. So if this current is I, it splits into a current I1 and I2. Okay, this is the situation. Now we can understand that what will be my I1. So if V is equal to V0 sine omega t like this, my I1 will be V0 divided by impedance of that circuit into sine omega t plus some kind of phase constant itself. Fine. And what will be my I2?
Can you please repeat what do we have to do in this?
We have to find the condition for I2 to be minimum. Okay, so I'm just showing the circuit in one moment. Okay, so we have to find the condition for I2 to be minimum.
सर एलसी पैरेलल में लोड रेजिस्टेंस भी होगा क्या?
Because you just said it's parallel circuit, na beta? The question that you sent me in email, that is talking about in parallel, na?
Yes, so LNC
The current is minimum in case of LC parallel circuit at resonance.
so इसमें LCR series में है.
So then why you asked about parallel?
So series के केस में current maximum रहेगा और parallel के केस
So
में
you are saying that inductor and capacitor are also in parallel, is it?
yes
Are you
LNC
talking about this?
yes LNC both are parallel.
You're talking about this.
Yes, and
This kind
that
of circuit.
and EMF yes. This.
Achha, just this kind of circuit. Okay, so that's a
Yes.
different question. Okay, so see that also. So if we have this kind of a situation now, and we have a current I like this, where this is I1 and this is I2. Okay. Now here you can understand the above circuit. If you write the KVL for the above circuit, the outer loop, you will get a simple capacitive circuit, assuming that resistance is tending to 0 and all that. So what we'll get for I1, we'll get I1 as V0 divided by this thing, XC. But what about the phase constant? Leads or lags? Lags, you know?
That's by pi/2.
Minus pi. And similarly, if you write the KVL for the battery or the voltage source plus the AC voltage source plus the inductor, that loop, you will get I2 as what? We'll get it as V0 by XL into sine omega t plus pi by 2. Okay. So what is the net current which is being drawn from the circuit now? That is I1 plus I2. So just do the algebra here and the rest should be clear. Okay. So just replace sine omega t minus pi by 2 with minus cos omega t, and this one with plus cos omega t. So your I is I1 plus I2, your junction law applied over there. So it is B naught into minus cos omega t divided by xc plus cos omega t divided by xc. So it is V naught cos omega t into xc minus xl divided by xc into xl. So this is the current. Okay. So ये current का जो peak value है वो कितना है, या जो ये current का जो RMS value है वो कितना है? It is V naught 1 by root 2 times the peak value. So V naught into xc minus xl divided by xc into xl. So now you're seeing the answer, na, beta? This RMS value is minimum equal to how much? 0. And that happens in which case? When xc is equal to xc. This IRMS is equal to 0 for xc equal to xl. Or that is omega is equal to 1 by root x. So this is the interpretation. Okay, now you can also try later the other question which I put up earlier. You can just make a side note of that diagram and see what interesting relation you get over there. But that's a more complicated question. It's more like a JEE Advanced level question. Okay, now I'll come back to one of Arman's questions. Kritika, you sent me another. Kritika, you sent me another question. I'll come to that also.
No, sir, that was not a question. That was just a diagram I wanted to show.
Acha, this one, the mail that you sent me, it has.
So both are different. No?
Oh,
This diagram and LC oscillator.
right. यही वाले question का था ना? Okay, right. No, see, when a question is talking about this thing, the resonance condition, that means there is a AC source involved. Okay, and because the resonance condition क्या होता है कि AC source का जो omega है, that should be equal to the natural frequency of the LC oscillator. So what is the natural frequency of the LC oscillator? It is 1 by root LC. So the resonance condition itself means that there must be a source involved. Okay.
Okay.
Yeah. Okay. So now coming back to yeah. So there's this good question about electric dipoles. Let's discuss about this from the questions that Arman has sent. Yeah, so both of you just go through this question. So you have two short electric dipoles. Short means the size of the dipole is negligible, okay, as shown. The energy of the electric interaction between these dipoles will be how much? You have to understand this. Okay, so the hint I will give you over here is energy of interaction is basically like a potential energy. उसका मतलब क्या है that if let's say initially I place just the dipole P2 and the dipole P1 is very far away, and then I brought P1 from infinity to that given point. So the work done by me will be the change in potential energy of the system, and that will be the interaction energy. Only the diagram is a little bit misleading. I'll make a better version of the diagram and you will understand. So is the question clear, people? So we come to our whiteboard here. So the better version of the diagram would be something like this. We've got one short dipole, let's say over here, which is my P1. And from the center of that dipole, at some distance r and at some angle theta, I placed my second dipole. Let's say over here. So this dipole is, I think, my P2. And this dipole is P1. And here, this angle is theta, and this distance is r. So r is very large compared to the size of either of the dipoles. So r is this from the center to center kind of distance. That's r. That's very large compared to this. Okay. So what we'll do is, first we will take the center of the second dipole as, let's say, a point P, or any point, let's say point Q, and we'll take the center of this dipole as the origin. So we will find or express the potential at the point Q, okay, due to the dipole P1. So what does that potential represent? It represents the potential at this arbitrary point Q, which is where I'm placing the second dipole, because of the charges present over here, the plus Q and the minus Q which are present over there. And that formula you know. Right? You know this formula, that potential due to a dipole is given by how much? It is given by K P cos theta divided by R square. So in this case, this P is P1. Correct? You are familiar with this formula, people? The general value of potential due to a dipole at an arbitrary point r theta, like this.
Yes.
Right. From this, you even have the electric field. The electric field due to the dipole, you write as the radial component times r cap plus the tangential component times theta cap. Where you know the formula that the radial component is minus del v by del r. So it becomes 2 kp cos theta divided by r cube. And the tangential component is given by the formula minus 1 by r into del v by del theta. So this is how we express gradient in polar system, in r theta system. So this becomes kp sine theta divided by r cube. So that's anyway not for this question, but this is an easy way of understanding electric field due to dipole. But now here I will stick to the potential only. So what the potential tells me is that at this center point Q, if I bring a unit positive charge from infinity to this point, the work I have to do is that much, that potential. And that will become the interaction energy of that unit positive charge with respect to this dipole P1. So now what I'm doing is I'm not bringing a unit positive charge, I'm bringing two charge particles. So let's observe what we are doing with respect to that point Q1. So now let me draw a sort of magnified version of this dipole, this thing that I've drawn, the dipole P2. So that dipole is like this, let's say. So this dipole is P2. And over here, its center is the point Q which I've taken. So I know the potential at that point Q is this much. It is P1 cos theta divided by R. Okay. Now, what was happening from that center earlier? This distance from the center of my first dipole, which I have taken as the origin, is R. So what about this point where I place the positive Q2 charge? And this point where I have placed the negative Q2 charge? They are at some distances, let's say L and L. where we know that 2 times Q2 into L is the dipole moment of this one. So that is equal to P2. And this is the additional information. Alright. And of course, L is very small compared to R. Because it was given to us that the dipole is very small. So is this magnified diagram clear to you guys? Because this is a bit complicated. This question is related to this. Is this diagram clear, people?
Yes.
Okay. So see, R is the position of the center of this dipole Q with respect to the center of the earlier dipole P1, which was sitting over here. So O से लेके Q तक जो position vector है वो R है. So now मैं क्या कर रहा हूँ? When I'm bringing the second dipole P2, I'm placing a positive Q2 charge where? Not exactly at R. I'm placing it at slightly beyond R at a distance L. And the negative charge I'm placing not exactly at R, slightly before, at a distance of L before. Okay. So now I will relate the potential due to that dipole at the point where my positive charge is placed. It will be basically what? It will be Kp1 cos theta divided by replace R with what? R plus L. Okay. Whole square. For which I can do a binomial approximation. This will become Kp1 cos theta by R square into 1 minus 2 times L square by R square. Are you getting this? I've just done a binomial approximation. Now, so take R
Minus
common
2 L by
so
R,
R,
right?
yeah, we had 1 plus L by R to the power minus 2. So it becomes minus 2 L by R. Not right. So this is approximately the potential at the position. This is potential due to P1 at the location of the positive Q1 charge. Sorry, the positive Q2 charge. That dipole's positive charge. The second dipole. Similarly, the potential at the location of minus Q2, that I'm writing suppose as V minus, that will be how much? Kp1 cos theta divided by R minus L ka whole square. So it's a very similar expression, but replace this with a, so that is Kp1 cos theta by R square into 1 plus 2L by R square. Correct? Okay. Now what I'm doing is I'm bringing plus Q2 to a point at which the potential is equal to V plus and minus Q2 to a point where the potential is how much? It is V minus. These expressions that I've just written. So my total work done by the external agent will become the interaction energy of the system. This will become the interaction energy. And that will become how much? It will be plus Q2 into V plus of minus Q2 into the potential at that point. So now just apply this. So it's becoming the interaction energy is becoming, you will take Q2 common, okay, and into V plus minus of V minus. So it is becoming, now you see the rest of it becomes very easy. It becomes Kp1 divided by R square cos theta, okay, into this one was how much? 1 minus this thing, 2L by R. Correct. So I can just do here is even take this term common. Just going up for a moment. So you can see this was like this and this term was like this. So minus of 1 plus 2L by R. Okay. So now let's see what we are getting. We are getting Kp1 cos theta by R square पहले बाहर common ले लेना into Q2 into what is left of this bracket. So what is left of this bracket is minus 4L by R. Correct? Okay. Now in this, remember what is Q2 into 2L? It is the second dipole moment. So it is P2. So keep aside 2L, so another 2 comes outside. So minus 2 times K by R cube P1 P2. This becomes the interactive potential. And you'll understand why it is interactive, because see, the way the orientation is, you will see that to bring the, see, the point that you've chosen, if you go back to the geometry of that point, P1 का जो positive charge है, that is closer to that point compared to P1 का negative charge. That means those points in positive potential. Okay? So you are bringing a negative charge closer to a system which is creating positive potential, then you are bringing the positive charge. So the negative work done to bring that negative charge is dominating over the positive work done to bring the positive charge. So that's why your total interactive energy is negative. Or in other words, the negative value of interactive energy is showing you that the system internally or the interactive force of the system is attractive. And again, the orientation of the two dipoles will show you why it is attractive. If you just draw the electric field lines due to the first dipole P1 and understand how the second dipole is interacting in that, you will see that the attractive force that is acting on the negative charge will dominate over the repulsive force that is acting on the positive charge. So this will have a tendency of having a component of radial force which is towards the center, not away from the center. So that's why the potential energy is negative. Okay, so I'm just going to minimize this a little bit further because it's quite a complicated question and take you through all the steps from the beginning. So we are making use of the concept of potential. We are making use of the formula of potential due to dipole, which is the important thing to remember, this formula here. Okay. And then we are doing some small distance approximation and binomial approximation. So this was the first step. Now understand that because of P1, इसके center पे potential कैसा होगा? इसके center पे potential will be according to this formula. So that's what we did next. That we made a sort of blown up diagram of P2 over here. So the center of P2 is Q, and it is at a position vector R with respect to P1 center. So at Q, this is the potential. But actually, I'm not interested in the potential exactly at Q. I'm interested at the potential at Q plus L and Q minus L. So that is these 2 points. The potential where the positive charge is located, B plus wala, and the potential where the negative charge is located. And then the rest is just approximation methods and all. So with bit of practice, all these approximations and things become easy for you.
Can you scroll down a bit?
Yeah, I'm coming to the lower part. Right, Arman, beta, this part is clear so far?
Yes, sir.
So I'm just bringing you to the final answer. Okay, like this. My mistake. This should be R cube here in the denominator.
Oh.
Yeah. Okay, so I think this is clear, beta.
Yes, sir.
So we move on to the next question again. Okay, so let's pick up some other question now. Okay, so there's this kind of conceptual question. So let's work this out first. Coming up on your board now. So right, so let's take a look at this question. 60th one here. Right, so it says that if electric potential while moving in a certain path is constant, then the electric field must be zero. Okay. So first of all, can you tell me is this valid? I'm saying electric potential while moving in a certain path is constant. So does it mean that electric field is zero?
No.
No, no. So statement 1 itself is wrong. Can you give me an example of how this will fail?
Cylindrical surface area.
Correct. If you have, cylindrical charge distribution, or even spherical for that matter. I have a spherical conductor और उसको मैंने थोड़ा charge दे दिया. So all the charge is uniformly distributed on the surface. Now on the surface of that conductor only, if you move tangential to the surface, or you just move along the surface, on that spherical surface, potential is constant everywhere, but there is field which is radial. Okay, so that is why statement 1 is becoming wrong. Okay. Now the other thing is component of field ER is minus del B by del R. So this statement 2 is correct on its own, right? Because that's how we express the gradient in radial system. So the radial component of gradient is del by del R. So the radial component of field will become minus del B by del R. But the thing is, does it successfully explain this thing? Does it explain statement 1 completely?
But statement
Because
one
we could
is statement 1 is already wrong, no, sir?
Right. Sorry, statement 1 is wrong.
D, oh yeah, it will be D.
Yeah. So this will only have correct. So there's no question of deciding that. Okay. So hope this is clear. So understood why statement 1 is wrong, no?
Yes, sir.
Okay, very good. Right. So I will come back to one of the questions by Ritika again. Unless I've covered all of them, not sure. I think few are remaining. Okay, so let's come to this question, this 21st one. Let me see if I can rotate it for you. Rotate it a couple of times, 3 times rather. Okay. So let us look at this 21st question next. Okay. So which of the following quantity does not change due to damping of oscillation? Angular frequency, time period, amplitude, initial phase. But angular frequency changes. Okay. And that's why time period also changes, and amplitude definitely diminishes. Okay. So if you remember the formula of damped oscillation, you will see that omega square for damped oscillation is not k by m. And it is k by m minus some gamma square, where that gamma is given by that term. Okay. So correct, understood now? So yes. If you just so damped oscillation के formula ना आप अच्छे से याद कर लो. Now that damping coefficient, it is given by c by 2m. That term where c is the it is a constant for the damping force. Okay. So make sure that you remember. The general equation is d2x by dt square, or m d2x by dt square is equal to minus omega square x minus c into v, or minus c into dx by dt. So from that you get the damping coefficient as c, like c by 2m and all that. So you should just understand that. So that's why what will not change is the initial phase. That's all. Rest of the things will be changing. So that's this question. Now let's come to this 26th question before we move on. So again, I will have to rotate it 3 times, unfortunately, but still. Okay. So this again.
So sir, that is cleared. That is cleared. Okay.
So I think your question set is done, beta. Kritika?
Yes. Sir, actually, yeah. last class, I was left with 5 more questions from the advanced sheet. So can you give me 5 minutes? I wanted to open the file.
Yeah, sure. You bring that. So in the meantime, we just couple of questions of Arman is also remaining. So let's work these out also. Okay. So Arman, the next question in your set is this one, this 18th one, right?
Yes.
Okay, so let's go through this. Find the force experienced by the semicircular rod charged with Q placed in the figure. Radius of the wire is R. Infinitely long charge lambda is passing through its center. So ये तो integration से हो जाएगा ना बेटा. So what you do is like what you do in this question is like, let's say your infinite wire, that one is lying along the z axis, right? And your semicircular ring is lying in the xy plane, with its center of curvature will be now at the origin. Okay, so let us view this diagram from the top. No, so the infinite plane is actually coming out for us in that case. Okay, so let's see how that works. So if we just make this a two-dimensional diagram with the infinite line coming out of the plane, it will be pretty easy to solve. So first, let's understand the actual given question. So you have, let's say, you have this infinite line of charge like this, and we have also some kind of a semi-ring around it. Okay, so this is my system of axes. Let's see. So this is, let's say, my XY plane. This is my Z axis. And this is actually going to infinity. This is actually going all the way to infinity, lambda. And there is a semi-ring of radius r, which I think has the same lambda. So this is the semi-ring center of curvature O, and it is in the XY plane. In fact, its diameter is along the y-axis. Okay. So we want to find the force on this one.
Yes.
This. We have to find this force on the semi-ring. Okay. So next, what we do to simplify the problem for ourselves is we look down the XY plane. Okay. So life becomes very simple once we do that. So the way I had selected this, the y-axis was the diameter of the semi-ring. So I have all this, and I have the infinite wire coming out like this. Okay, so the infinite wire at every point here is creating field like this. Radially outwards. And since this radius is r, so the magnitude of field at each of these points on the surface is how much? Lambda by 2 pi epsilon naught r. So now, let's zoom into this a little. So now if I take on this at some position vector, like this over here. I take a small element.
Achha, okay, and then integrate and only the sin theta term will remain.
Correct. In my case, I like this only cos theta, but
cos theta will
you can take from minus plus pi by 2, or you can take that one and like this. So
okay.
यहाँ पे r d theta होगा length में.
हाँ d theta हो जाएगा.
तो उसका जो charge होगा dq, that will be lambda into r d theta.
हाँ.
And the field is like this. So that element will experience, in zooming out, that element will experience a force which you can very easily calculate.
Okay.
So that element will experience a force, let's say df like this. So that df's magnitude will be Just a moment, my board is frozen. So, but you just have to wait a minute till it comes back. So what happens is you just write df as dq into e, and then df cos theta you integrate from theta equal to minus pi by 2 to plus pi by 2, and you will get the net force along the x-axis.
Okay.
Well, Arman, I think you'll be able to solve this.
I'll try.
Okay. Guys, just a minute, okay? I'll have to reboot this system. So till then, I'll put up the next question, and so the next question we'll do is this one.
Sir, can you please solve the bit more?
Can I what? Sorry.
Can you solve this?
Yeah, I'm going to solve this better. Just that my system has unfortunately got hanged. So you'll have to just wait a minute, okay? I'm rebooting it now. But for your benefit, in the meantime, I'm also putting up the other question. So you can go through that. Then I'll come back to this question.
Okay.
Okay, so we'll come back to that question in a moment. Just a second. Okay, so right, so right, so coming back to this here. So you understood up to that element that we've drawn, Kritika? So यहाँ पे
Yes, sir.
with that element dq, which is given by lambda r, so that force that that element is experiencing, that force is, let's say, df, that is this vector which I've drawn over here. So that df has a magnitude of e dq. So let's replace that first. So E is lambda by 2 pi epsilon naught r. This is a constant, okay, but into that lambda into r d theta. In the question, both of them had the same lambda, so it's like this, okay. So it is lambda square upon 2 pi epsilon naught into d theta. That is the force itself. But now you can see that the force has a cancelling component and an adding component, because an element over here will experience a force df like this. So you can see the y components will cancel and the x components will add. So that is why my net force will ultimately act in which direction? It will act along the distance. It will act along the positive x. So my net force will be the integrated sum of all the cos theta components, the way I have drawn theta, right from this point, let's say E, right up to that point above, which is B. For all the elements from A to B. So that will become lambda square by 2 pi epsilon naught cos theta d theta, integrated from the point A where theta is minus pi by 2 to theta equal to plus pi by 2 point. And you know that cos theta from minus to plus pi by 2 will give you 2. Okay, so you know that your net force actually become lambda square by pi epsilon naught. Because cos theta gives us 2. Okay. So this should become your final answer. Okay, so Arman, I'm just navigating to your next question. First, I'll just minimize this for both of you. All right, so is this clear, people? Can I move on to the next question now?
Yes, sir.
Oh. Okay, so let's see this question now. 40th one. It says diagram shows 3 infinitely long uniform line charges placed on the x, y, and z axis. The work done in moving a unit positive charge from 1, 1, 1 to 0, 1, 1, okay, is equal to how much? Okay, so you are moving particle from somewhere on the positive quadrant for all the 3 planes, x, y, y, z, z, x, like that, to a point which is lying with its x coordinate as 0. So it's lying on the yz plane at 1, 1. Okay. So this is a very interesting type of question, because what is happening is why this is slightly tricky and a very interesting type of question is because for an infinite line of charge, as you know, we cannot define absolute potential. Now, there is no formula for potential at a point at a distance r from an infinite line or something. Why? Because the charge itself is infinite. So there is no reference that at infinity the potential should be 0. Okay. However, we can define the potential. We can define the potential difference between 2 points by using the formula that delta V is minus E dot ds integrated. So that is the concept we use over here. that let's say the point 1 comma 1 comma 1 given to us is point A, and the point 0 comma 1 comma 1 is point B. So you're moving a particle from point A to point B. So the potential difference VB minus VA, we'll have to understand it as minus E dot ds integrated, or negative of path length integration of electric field from A to B, where the electric field is the cumulative sum of the electric field due to the three rods. Okay. Now, as you can see, the field will be three-dimensional, because the rod which is along, or the infinite line along the y-axis, will be creating a field in the xz plane. The one along x-axis will be creating a radial field in the yz plane, and similarly the z1 will be creating a radial field in the xy plane. So how do we come up with this integration, and what's going to be the easy way of solving this? So for that, first of all, you understand the thing that we are dealing with a conservative quantity. Electric field is conservative. So minus E dot ds integrated is going to be same for all paths. So first of all, try to select the simplest possible path between the 2 points given to us. So draw a straight line between the 2 points, and then try to calculate the work done against the electric field, or minus E dot ds along that straight line, and you'll see you'll come up with something simple. So it's about understanding this understanding the three-dimensionality. So what I would suggest is, see, the 2 points A and B are given as some point in the general positive quadrant of all 3 planes to some point on the yz plane. So the straight line will be how? The straight line will actually be parallel to the straight line will in fact be parallel to the x-axis, because you're going from x equal to 1 to x equal to 0, while your y and z coordinate are remaining fixed. So the straight line that you're moving from A to B will actually be parallel to the x-axis, but lying somewhere in space like that, between the 3 coordinates, or in the positive quadrant for all 3 planes like that. So first of all, make that straight line, and then visualize that straight line in any one of the 3 planes. Like look down the y-axis or look down the x-axis, or x-axis will not help because the line is parallel to the x-axis. Either look down the y-axis or look down the z-axis and visualize that straight line and see how the electric field lines are cutting it, and you will understand very easily how to do this. So I'm coming to it in a moment, but this is quite an interesting problem because of the three-dimensionality. So I want to be able to first try making the diagram that I'm telling you. That label the 2 points A and B which are given, and you'll realize that the 2 points, if you join them by a straight line, it's actually a line parallel to the x-axis. Okay, so now you visualize that line either looking down the z-axis or looking down the y-axis, and try to understand how it's looking, and try to understand the field at any point on that straight line, so that you can carry out the integration minus E dot ds along the straight line from A to B. Are you understanding my points?
Yes.
Okay, so just make that diagram. I'll put it up in a moment. Okay, so let me just take you through the diagram I was talking about. So don't worry about the electric field lines in this diagram, because the three-dimensionality of that means that they are pretty complicated. But there is an easy way of writing them, so don't worry about that. So like this, let's say. So this is my XY axis, my origin, and this is my Z axis. Okay. Now you'll see that here it's pretty tricky to visualize this, but my point A is lying somewhere over here because it has all three coordinates positive, and my point B will lie somewhere on the YZ plane. So if this is my YZ plane, the point B will lie on it because it's having X coordinates 0, 1, 1. So this straight line, first I'll visualize this from top. So now let me visualize that straight line looking down the y-axis. So looking down the y-axis, I'm seeing the x-axis like this, and I'm seeing the z-axis like this. And in this diagram now, somewhere here is my point E, which is 1, 1, 1, and somewhere here is my point B, which is 0, 1, 1. Okay. Now in this diagram, it might look that why I have not taken its y coordinate as 0, because this point is actually not lying in this plane; it's lying above this plane. You understanding your point? So actually, A and B lie in a plane which is parallel to the exact plane. So when I'm drawing the straight line joining A and B, you have to understand that the line AB is in a plane parallel to the XY plane, sorry, the XZ plane. Okay. At y equal to plus 1. It's above the XZ plane at y equal to plus 1. Okay. So now what I want to do is I want to calculate VB minus V, potential difference. So that is going to be nothing but minus E dot ds. Okay. So that potential difference from U2. Okay, so now let us start worrying about how we will take this thing, the path integration. So I'm magnifying this diagram a little. So somewhere on this path, okay, let us take an arbitrary point and let's draw a small displacement vector over there. At a point like this, let us draw the displacement vector ds. And the position of that point is this one. So this is the position vector of that point R. And that point, let's say some general point P, and it has what kind of coordinate? It has x coordinate, which is varying, is going from 1 to 0. Y coordinate, which is fixed, which is 1. And z coordinate, which is fixed, which is 1. Understand? So the x coordinate is between 0 and 1 as you're going along. Okay. So now let us understand the electric field at the point. Okay. So my ds, first of all, in this diagram is basically what? From the diagram you can see you're moving along which axis? You're moving only along x axis. So your ds will be nothing but dx I cap. Your y and z coordinate are remaining fixed, assuming the numbers. And notice I have not written minus dx I cap because the limits will take care of direction. That is, at a x equal to 1, at b x equal to 0. That takes care of direction. So whether the direction is positive or negative, that is taken care of by the limits. It's just the important thing is that the line is parallel to the x-axis. So your ds is some dx I cap. The limits take care of the fact that dx is a positive quantity or a negative quantity. Now let's come to the more important thing. At the point P, which is x, 1, 1, what is the net electric field? So this electric field is the field due to the x-axis wala line plus the field due to the y-axis wala line plus the field due to the z-axis wala line. Understood the point? So there is a line of charge which is lying along the x-axis, infinite line of charge. So that is creating some kind of field at this point, which will be actually pointing away from it. So it will be along the some kind of direction like this. Similarly, there is a line of charge here, and there is a line of charge along the z-axis. That is going to create some field which is like this. Okay. Now see, because of the three-dimensionality, it is becoming very complicated. Okay. However, if you move this diagram to the distinct plane, so if you visualize the field because of the line along the x-axis, how is your motion happening compared to that field? It is happening perpendicularly because the field because of your x-axis is always lying in the yz plane. Okay, so they are radial lines with respect to the x-axis, and your motion is what? Parallel to the x-axis. So Ex dot ds, that is your electric field due to the x-axis. Okay, this is not the x component of electric field, but this is the field due to the x-axis line of charge. Similarly, this is because of the y-axis line of charge. This is because of the z-axis line of charge. So now you will realize my point that Ex dot ds will be 0. Why this is the case? Because see, ds is along the x-axis. Okay. And the field because of charge on the x-axis is radially outwards from the x-axis. No? So they are perpendicular. So these two are perpendicular to each other. So their dot product is 0. Is this point clear, Aman and Ritika? Right, guys. So hope this point is clear to both of you.
Yes.
Okay. Now what about dy?
सर इसमें ds वेक्टर कौन सा था? I mean
ds vector
diagram.
was the displacement from A to B. This one. Right?
अच्छा, okay.
Right now. So actually now you have to visualize this from this side. So draw a cylinder around the x-axis. So this AB line is actually along that cylinder surface. You understanding? Is parallel to the axis of the cylinder and on its surface. Whereas the electric field lines due to x are coming out radially. No? So the dot product will be 0. Right? Is this clear?
Yes.
Okay. Now, what about because of the z-axis? Because of the z-axis, the field will be in this sort of direction. Right? So, that will make things a little complicated. So what I'll do is, I'll tell you another way of doing this. Okay. Now see what is happening. Let's say I have 3 lines of charge x, y, and z. Abhi you can see x ke wajah se there's no potential difference between these 2 points because Ex dot ds is 0. Now y and z ke liye kaisa hai? Let's calculate. Okay, so let's calculate it this way. So let's understand separately. Okay, potential difference near an infinite line. How to calculate that? Okay, so let's say your infinite line is coming out of the plane. Okay, so let's say this is your infinite line coming out of the plane. So your field lines are looking like what? They are looking like radial lines like this around it. So that means what are your equipotential surfaces? They are cylindrical surfaces. You following my point, people? For an infinite line of charge, what do equipotential surfaces look like? They look like circles. I mean, they look like cylinders. Arman and Kritika, is this correct? Is this clear?
Yes, sir.
If you visualize this in 3D, what I'm trying to say is, in 3D, if you have an infinite line like this, so field line this is radially bar, na? So what is your equipotential surface? It's a cylinder like
Okay,
this.
okay.
Like, so if your cylinder has radius, one cylinder has radius E and another cylinder has radius B. So what is the potential difference between these two? That we can calculate. Okay? So VA minus VB will become what? Lambda by 2 pi epsilon naught R into dr by integration from R equal to B to R equal to E. Now the cylinder which is of smaller radius will be at higher potential. So that's why I've taken VA minus VB. So you get that ln kind of term. You'll remember this from certain questions also. 2 pi epsilon naught ln B by A. This is the potential difference between A minus B. Correct?
Yes.
Okay. So what this is telling me that if I go from any point on this cylinder to any point on this cylinder, via any path, it doesn't matter. The potential difference will be this. Or in this diagram, if I go from one outer cylinder, which is of radius B, any point on this cylinder to any point on the inner cylinder via any path, this is the potential difference is creating.
Okay.
You understanding the point? So now come back to my question over there and see. So x-axis we forget about because x-axis ki wajah se there is no potential difference we are creating. Now think of the z-axis. So the z-axis was like this. So this was the z-axis, and we are moving from a point A to another point B over here, where the point B was how much? It was 0, 1, 1, and the point A was how much? It was 1, 1, 1. So ये point B का perpendicular distance from the z-axis कितना था? Let's say that was B. That will be 1 only, right? See this coordinate 0, 1, 1. At what distance it is from the z-axis? It's at 1. Okay.
Yes.
Whereas this one is at a distance of how much from the z-axis? It is at a distance of root 2. You're getting it? So if you visualize this from above, this is your z-axis. Draw a circle of radius 1 around it, and then draw a circle of radius root 2 around it. So your point, okay, and in this is your x-axis and all that. This is maybe your y-axis, whatever. So your point A is lying over here. This is your z-axis. So your point A is lying over here. So it is at a distance of root 2 from the center. And this is your point B is lying over here. So this is at a distance of 1. And this is that line AB that we are talking about. You understanding this now? So VB minus VA, just because of the z-axis line, okay, just because of the z-axis line, will become how much? It will become lambda upon 2 pi epsilon naught, okay, natural log of A divided by B. Because you're going from a point which is further away to a point which is closer, so your potential difference should be positive. So be lambda by 2 pi epsilon naught ln of root 2. Is this
सर
clear?
एक डाउट है
हाँ बताओ बेटा.
सर अगर हम लोग तीनों के तीनों लाइन से एक पॉइंट पे नेट पोटेंशियल जैसे पॉइंट है वहां पे तीनों लाइन के वजह से आपने पोटेंशियल निकाल दिया, देन बी में आपने पोटेंशियल निकाल दिया.
See, the problem with infinite line of charges, you cannot calculate absolute potential. You try and do that, now you'll end up doing ln r integrated from infinity to that point. So it's undefined, na?
Oh, yes, sir.
So that is why we have to think in terms of potential difference. We cannot think in terms of potential. So you always finite line ke around, you imagine you have those invisible cylindrical shells, and each shell is at some potential. Okay. So the potential difference between two shells is some constant into ln of b by a.
Okay.
So now you visualize this point A and this point B, what kind of shells they are lying on with respect to the z-axis. So you'll realize A is lying on a shell which is of radius root 2, whereas B is lying on a shell which is of radius 1. Got my point now?
Yeah.
So as far as just the charge Z is concerned, उसकी वजह से कितना potential difference create हो रहा है, इतना potential. Okay. Now similarly, if you visualize for the y-axis, you'll get the similar thing. Now your y-axis is lying over here. And your point B was over here lying on the xz plane, on the yz plane. So it is at the point 1, 0, 0, 0, 1, 1. Okay. And your point A was lying somewhere over here. So again, you can see the perpendicular distance of point A is root 2 from the y-axis because it's 1, 1, 1. And the perpendicular distance of this one, B, is nothing but 1. So it's the same situation for the y-axis also. You're going from a point on the surface which is of radius root 2 to a point on the surface which is of radius 1. So again, the potential difference between these two created because of the y-axis is also the same. It is lambda by 2 pi epsilon naught into ln of the outer radius which is root 2 divided by ln of the inner radius which is 1. So it is ln. Okay. And same thing if you now visualize with respect to the x-axis, you'll see both these points are lying on the same shell. That's why the potential difference because of the x-axis is 0. You understanding my point? So now the net potential difference, it is your this thing. It is
Sir, x-axis के respect में कैसे होगा?
X-axis के respect में you will realize both these points are lying at the same radius. Because what is this point's distance from the x-axis? It's root 2. What is this point's distance from the x-axis? Again, it's root 2. You understand? Yes. No? See, the general coordinate geometry we are using, if you have a point P which is x, y, z, okay, coordinates, what is its perpendicular distance from, let's say, x-axis? It becomes root of y square plus z square.
Yes.
What is its perpendicular distance from y-axis? It's
x
root
square
of
plus
x
z.
plus z. So that coordinate geometry. Okay. So that's why this becomes x square plus y square. So just using this general principle over here. So that's why you'll realize that because of the x-axis charge, there's no potential difference created. But these two are creating the same. So it is lambda by 2 pi epsilon naught ln 2 or ln root 2 plus again the same thing, lambda by 2 pi epsilon naught ln of. So your net becomes this thing. So you can even take the power outside as half. So it will become lambda by 2 pi epsilon naught ln 2. Alright guys, so hope this is clear.
Yes.
Okay, so the learning from this question is that actually, even though we cannot calculate potential difference because of a line of charge, we can always calculate the potential difference between 2 points, which are at a distance of E from that, because they are lying on two different equipotential surfaces. Okay, and then we use that along with superposition over here to find the individual potential difference because of one line, because of second line, because of third line, and do the sum of the two.
अच्छा सर मतलब ऐसे क्वेश्चंस में मिनिमम 2 पॉइंट्स होने चाहिए.
हाँ, मतलब actually the distance at least from one of the lines should be changing, no? Otherwise there won't be any potential difference. Got my point? Okay. So people, we'll have to conclude here today because I have another session coming up. But hope at least most of your doubts have got cleared.
Yes, sir.
Anything remaining during the week, you can just send me a WhatsApp. I'll try to send you a solution sooner or later. Okay,
sir. Sir, you will be sending the recording and the whiteboard?
Yeah.
Yes, okay.
Yes, both the video recording as well as the whiteboard I will send to you. Okay, beta?
Okay, thank you.
Okay, so that's it. Thank you.
Thank you, sir.
Okay, all the best, beta.
Thank you, sir.